All right, folks, this is the last concept you need to learn. And then you just have to demonstrate it on some exams, and you're done with this class. Congratulations. So we have this notion of a z-score. And I don't know if you've all heard of the ACT and SAT. They're two different companies, two different college entrance exams. I forget what Michigan's using. I think we went to the ACT. We used to be the SAT. This says, are they normally distributed? We're going to say, yeah, they probably are, because everyone gets instruction and everyone has different test taking abilities. And on average, most people are going to do relatively well. Some are going to do really well. Some are going to do really bad. So we can just assume that they're normally distributed. The problem is, if you took an ACT and SAT score or test and got back your scores, like the ACT, last I checked, was out of 36 points. So if you scored a 36, you had a perfect on that exam. And the SAT is like with a 3,200 or something, or 3,600 or something. So how would you compare those two scores and determine who did better? Well, one way to do it is just compare how far from that exam's mean is your data value. So is it far from the mean, above, or far below? And the z-score is that exact measure. It's the number of standard deviations a particular data value is from the mean. So here it is in your textbook. A z-score tells you how many standard deviations a data value is from the mean. All right, so how do we calculate it, or how does that look? Well, if you jump to the next page and you think about a z-score, how far away would the mean be from the mean? And you're like, what? That's a crazy question. And I agree. This would be 0. Well, if we're one standard deviation away above the mean, then the z-score would be a 1 at that point. If we were a 2, it would be a 2. And if we're 3, it would be 3. And then same thing in the other direction, except they're just negative. So if you look back at one of our original normal curves, it looked like this. We had x's and we were told the mean, so we plugged it in, and then we added a standard deviation above and subtracted for below, and we got these values. But when we work with z-scores, we convert all of our data values into a distance from this middle, from the mean, and so the mean becomes 0 when we convert all the data values to a z-score. And then the standard deviation becomes 1. So let's apply this. Turns out standardized tests of intelligence are scaled to an IQ of 100 with a standard deviation of 15. So find the z-score for a person with an 85. Well, if I know that this was the mean, and that was 0, and then I added 15, I know that this would be 115, 130, 145 above, and subtracting, I get 85, 60, and 45. Oh, there's our answer. A person with an IQ of an 85 would have a z-score of -1. A person with an IQ of 115 would have a z-score of 1. And then if we were like, hey, what's the probability that a person has an IQ between -1 and 1 in terms of z-scores, or as an x value between 85 and 115? Well, that's just these two numbers added together. So 34.1 plus 34.1, that's 68.2% chance that that happens. So if we have a data value has a z-score that is 0, half the data is above and half is below. In fact, that data value is the same as the mean of the data center. Okay, so let's get to like, what if we don't want to have to fill out this whole thing and we just want to take a data value and calculate its z-score? Well, there's a nice little formula. Here it is. Z equals x minus x bar divided by s, or x minus mu divided by sigma. Well, this is if our data comes from a sample. This is if it comes from a population. I like to write this formula as the z-score equals the data value minus the mean divided by the standard deviation. And that encapsulates both of these, because whether it's a population or a sample, the numbers that we're going to be using are the same. It's just we just have to determine, did the data we're working with come from a population or not. So let's practice this calculation. Here we've got the ACT has a mean score of 22.2 and a standard deviation of 5.1. And then the SAT in that same year had a 1498 for its mean and a standard deviation of 347. So who did better? A person who scores a 26 on the ACT or a person who scores an 1800 on the SAT? Well, here's what we're going to do. We're going to identify the different things that we have. So I'm going to do mu. I'm going to write mu, and I'm going to do a subscript A for ACT, and that's equal to 21.2. And I'm going to do sigma A for ACT, and that's 5.1. And then we're going to calculate a z-score. So the data value we're going to work with is that student that scored a 26 on the ACT. And then over here, I'm going to do mu S for SAT, and that score was 1498 for the mean, and that sigma S is 347, and the data value that we're given is a student that scored an 1800. So what we'll do is calculate the z-score for each of these, and then we can see which z-score is better. So for the ACT person, I'll do ZA as my subscript. That's equal to the data value, which is the number we were given for the particular student, minus the mean of all students that took the exam, divided by the standard deviation of all students that took the exam. So 26 minus 21.2 divided by 5.1, I'm getting, okay, let's try that again, divided by 5.1, I am getting a z-score approximately equal to 0.941. You need like 2 or 3 decimal places. I'm going to stick with 3 here. Be mindful of whatever Connect Math asks for, because that's the only way you can get it right. Okay, so for here, we're going to do the same thing. It's just that our statistics are different. Our data value is 1800. Our mean is 1498, and our standard deviation is 347. This turns out to be approximately 0.870. So if we look at these two z-scores, the student on the ACT did better because their score is larger. Not by a whole lot, by the way. It's kind of a small amount, but still slightly better.